Hi, everyone. Welcome. I am Sehyo Chang, and I'm a CTO and a co-founder of a company called Infineon. Throughout this event, we have many insightful presentations about how the WebAssembly is changing the IT landscape. Today, our focus turned into slightly, but in different area, a role of how WebAssembly is potentially changing in terms of impacting to event-driven application, especially real-time services, and toward building a next generation of compute engine using a component model. All right. So agenda is first we'll go over the basics of streaming computation, and then say why the WASM component will be useful in the area. Then go to a high-level design decision on why some of the design was made that way, and then how we actually translate into component model. And I'll sprinkle with some real-time demos and see if that works. Right. So we'll start with what is a stream computation. Okay. So in traditional IT data sort of a pipeline is that you feed the data into a data lake or database, a central. And then you pull the data using either a manual process or application. And then further down the line, another application and pull that data from that, another application. So the problem, unfortunately, is that that's very inefficient. It takes sometimes days and hours and days and years to get a very insightful analytics. And that translates that into meaningful business outcomes. Because you don't want to deal with the stale knowledge about your competition, and especially about changing the world. Okay. So the way to solve this problem is thinking in terms of everything as a stream. Because the root of the cause of this issue is because we're treating the data as the static items. In reality, data is ever-changing. Whether you're talking about your stock market prices, how your customer is purchasing your products, their habits, all those are changing in real time. So to deal with this one, you have to treat the data as a really dynamic environment. And so that means treating everything as a stream. So instead of putting that into a data lake or databases and sitting there for hours and days, you compute that as on the fly. So you turn one stream into another stream and using an approach called stream processing, which is to compute that on the fly. And potentially that could be further down enriched using a machine learning model or some kind of AI algorithm and turn into meaningful insight. And that turns into very low latency. So we are talking in terms of minutes and seconds instead of days. Okay. So to really concise to turn into what does means of a stream computation is turning up events coming in because a stream is made of events and converting to another events. But really the heart of it is a state. Without the state, you cannot do aggregation, which is basically the heart of any kind of analytical computation. Okay. So with that, you could build things like a delivery pipeline, where if you have app-based delivery, you are taking an order of events from the customers and turn the raw ingredients into food that gets delivered to the driver. Nowadays, you could actually deliver that to drone in other kind of automated vehicle delivery. And then you need some kind of dashboard to figure out whether everything is happening and whether you are actually making money or not. So in order to do this, you have to think in terms of how actually the data flows from the source to sink, and what is the latency involved, and what kind of analytics that requires. Okay. Now, one of the big issue with using streaming, trying to into traditional data pipeline is that most of the streaming applications now done through what you call big data streaming. So traditional Java-centric, and these are pretty much the most popular framework, Spark, or Apache Flink and Beam and Kafka, and they're very Java-centric and requires a lot of complexity. And not only that, but they're resource-heavy, and then also they're not designed for really edge. So you couldn't put that into embedded devices or many kind of resources where you have a memory and CPU constraints. And then there's a lot of talk about advantage of WASM in this conference, so I'm not going to go down into really that advantage, but it's obviously that the WASM could be useful for solving these kind of challenges. Okay. So basically, the biggest, I think, is the benefit is one is across language, because a lot of this big data framework is based on Java. So if you want to use like languages like Swift or Ruby or other languages, there's a lot of challenges integrating that, and we want to make a streaming popular, and we need to democratize such that anyone can use those, treat those streaming as really easy to pick it up and can be used by any developers. And not just that, but also deploy it everywhere, ships, boats, trucks, anywhere. And that also the WASM now brings that all the isolation and security benefit, and with the potential of the work, the component registry, now you can potentially package those WASM components if we do it properly, and can distribute it everywhere. Okay. So idea is take this stateful streaming computation and then map to WASM component. And now the challenge is how do we actually go about doing this? Okay, so we'll talk about some high-level design decision. So we start with some of the basics about how do we actually dealing with the streaming computation. The good thing is that a lot of this fundamental how about dealing with the streams are actually well established. So this is a fairly well-known 2015 Google paper about how to actually deal with the streams. So Google spent quite a bit of tremendous amount of research into how to actually building that compute that on the fly. And basically, there's 4 different areas of addressing this. One is how do we actually map this into a set of patterns, and then also building this operation into what you call DAC as a set of DACs, a set of DAC operators, and then also dealing with ordering, because when you're dealing with the streams, events can be coming out of the not usually in order, because when you are talking to embedded mobile devices, when you're dealing with other compute resource, you can get all of things out of the order line. So it's really the hardest part of it is conceptualizing what does it mean to synchronize these events. And because when you're dealing with the analytics, you want to make sure that everything is on that your analytics make sense. Okay, so the basic approach is the way we did it was we have this now tool called SSDK. So that's the framework that maps this stream-based computation into into the WASI and WebAssembly components, map into it. And then that we built in terms of Fluvio, which is our open source streaming engine that we actually built before. So we're actually using that to map underlying streaming. And then we built this new engine to map this streaming computation. Okay? So we start with the operators. So the operators are basic, the fundamental ingredients of how we actually transform these streams. So those are the basics like mapping, right? One mapping of one data to another data, filtering, that if you have encounters of events, you want to drop those events, or map one event to many events, which called flat mapping. And then other things like partitioning, because when you deal with events, it could be massive. So you want to divide that into partitions so those streams can be processed parallel. And then also the timestamping, which is a way to dealing with times. You divide that into these windows. And then after that, you maybe want to aggregate it, grouping, sort it. Okay. So here's one, probably the most immediate problems. Because when you're dealing with this kind of operation patterns, like mapping, you're mapping string to strings, numbers to strings, or money to profit. You're mapping essentially data types. So the question, so that in terms of a traditional streaming API, it's all generics. So first problem is that we try to model that into width is, of course, the biggest, the barrier was the lack of a generics in a width. Because the width is flat services. So if you have a service like mapping of uppercase to strings, you have to lay out this in a flat manner. Unfortunately, then we want to, of course, have to repeat this one. Then how do you actually dealing with all this different variation? So then kind of realization is just the component model is just beginning. So think of this component model as the basis for building other kind of abstraction on top of it. And then that brings the quote that had Kelsey Hightower that had a while back, which is for Kubernetes. Is Kubernetes is a platform building for platform. So now realize the WASM is OS for building the OSs. It's a start, not the end game. So it gives us abstraction to build the next generation of services and kind of new kind of compute platforms. Okay. So what we the initial SSDK abstraction is that we are going to start building this kind of DSL to build this abstraction. So for example, in here we have transforms that operator map, and since we know that this is a mapping, and we know that takes a single argument that turns another single argument, we can actually conceptualize and we can actually do the marketization. And that actually, we turn that into the width. So we use this to generate so width becomes another a layer that we can actually manipulate. Just like width has been to mechanize how we deal with the multiple language, we can build another set of a more level abstraction dealing with, for example, stream-based computation and other kind of abstraction that we can build on top. All right, so now let's just do the quick demo. Let's see if this works. All right, so here's a simplest operator that maps single strings into, we actually do capitalize. And with this our SSDK, you can actually inline, and here we just happen to have a Rust code. The idea is that we can support different languages here, and that will translate that into a width and with a WASM component. And SSDK will actually schedule it and run, and we used WASM time underneath. So we'll start this one here, and we run SSDK run, which we actually compile this into the width components and run it. So you see component here. And then what we're going to do is so Fluvis is the underlying the streaming message queue input. So we go here, and we have okay. So we have a producer that will send an event. Then we have another that we listen to this output event. So we say ABC, and you can see here we translate it into ABC right away, and that actually calls the WASM component and using a with to translate all this underneath and come back and send it to the streams. So this is like a hello world, and here another word. Let me see. So Apple here, and now we can actually now do here a simple case. So let's change this to another message to lowercase. So we're going to actually do this on the live. Okay, and let's see if that works. We save it, and we actually run again. And we go here, and this is like a test, and turns into lowercase. Okay, so this is the simplest that we have, and actually, so this also I can see the other thing is that we have the types here. So we can actually define the stream and define this happen to be a very simplest here, a string type. Then we map here and we define it. And we can actually define different types of operators. So that's here. Let me go back to presentation. All right. Then the next, we talk about states. So the states is actually the heart of the streaming computation because the states are durable. It means that when you have a crash, it automatically recovers the previous state and resume that the same data point. And the states are also append only, which means it's immutable because once you capture the state, you should not change. But you can actually append. And so the values may be changed, but you can go back to the previous in time and recover and replay back. Currently, we support key value, and I'll talk about those kind of what kind of the state can be the representation of a simple or raw value. Right. So here, the good thing is, so the way we map the state is we use the resource in a WASM component. The resource is how actually the WASM used to model like the sockets file system. But instead of doing that, in SSDK, we actually use that to model the state. Okay, so this is a simple to drawing of a state. So suppose we have simple city temperature value. And so Paris has a 55 degrees. This happens to be Fahrenheit, not Celsius. And the Sydney has a 70. So this is the simplest possible values, what you call scalar values. And then we actually, if you can see this one here, we have this called state here that actually represent these values. Then we compile this into with the resource value, the get and set value, and then you can increment it. And we actually also translate those into with types as well. So we actually do orchestrate all this type representation from the simple high-level abstraction. Okay. So this is another representation of actually using the with as the way to represent more complex representation. Okay. All right, so let's do another demo. Okay. So the same scenario here, except now we're going to count. We're going to count how many words that we actually done here. Let's see here. Okay, so we run this one here. So now the difference is now we have this show state. Okay, you can see it. There's nothing here because we haven't done anything. So now let's go into the same thing we've done before. Input. and output. So let's say Apple. Okay, and here you see this was Apple 1, because when we do show state here, we're actually capturing the states and we mapped it. So when we actually do show state, uppercase, count, put here as state. See, it says Apple and the value is 1 because we are actually doing a very simple representation. Now we do another Apple, and here we actually, what happened is that we actually increment 1 and put it here, and you see that it happened to be 2, and we go back to the same state here, and it shows 2. Same thing, we do banana, and here 1, and if it's here, we actually have banana here. Okay. Now, the interesting part is that the state is durable. So if you go and quit, and when you come back, we replay those events and restore the state as was before exactly. So here, you say exactly. And you can resume the bait and you can replay back. So that's the state is it's not just a simple memory-based value, but it's a durable and it's designed to recover from the failure and to replay, and you can also go back to the previous state based on the previous time. Okay. Right. To here. Right. Now we're going to more complex. So before it was a simple state. Now we can actually represent multiple values. So this is an example where if you want to capture, for example, like a number of flights, a statistic about the passengers on the airport. You know. So CDG may have a flight 450. So this is accumulated, right? So as the new flights coming in, we are adding more values to it. So we split that by this key here, CDG, airport, and San Francisco, and of course, Barcelona. And then when you have this key value, split value, we can actually then also now do aggregation. So that means we can actually look in all the state as a single entity. So here, we are using just called data frame. So the data frame is kind of a fancy word for the table. So here, you can actually see the key value, Barcelona, San Francisco as a key, and you can see the flight and passengers and freight. And here, then you can do actually very more complex operations. So, and the data frame, now the interesting part of the data frame is we actually use Apache Arrow as underneath representation. Apache Arrow is a columnar representation for data frame. So the column frame means that we store these values by the column instead of row. So in traditional Postgres, all the rows are stored one by one, but in a column representation, we store the column first. Advantage of that is that you have a huge amount because you can do the vector processing of those queries. It's typically about 10 to 100 times faster. And you can actually perform a huge amount of computation in it very fast. Another benefit of Apache Arrow is that it's becoming a standard. So a lot of ecosystem, data ecosystem use Arrow as now the standard way to represent values. So easy to actually can integrate the state into different kind of other tools and in ecosystems. Okay. Now, there's actually two ways to do this, handling this arrow representation. So those states are in a host here, and there's actually two ways to go about it. So one is we copy those the arrow memory column into the guest, or we do lazily run from the client. For the first generation of what we're doing is we're actually going to copy that into the client. That's much easier to handle it because doing the lazy is still a lot of the challenges we have to overcome. So the first generation of project we're doing is we're actually copying this on the fly. And it turns out that most of the time it's not too bad because when you're dealing with the stream-based computation, the amount of data is hopefully it's small enough that we can actually do it in an efficient manner. Okay? So that actually, we actually use the width to represent arrow chunks. So we actually represent these columns. And then we actually represent these arrow chunks in a width here, this arrow, because they're column based. Each of these different numeric representation is by itself. So you can actually copy all this array one by one and reassemble on the fly into guess. So what happened then is then we can actually in the guess component we copy this arrow in the guess memory. Then we can actually run any arrow compatible library, like Pola is a very popular arrow library, and access it directly. And then you can actually run this business logic just like you're doing in Pola. And here, this is a simple way to do a select statement, basically. And you can perform any kind of data frame operations inside. Only constraint is probably a memory. Okay, and that's the last demo. Let's try that. Okay, and here is actually just one more here. The same thing we do here. Okay, so we run here, and here we show nothing's here. And then what we're gonna do is consume. Actually, what we're gonna do is we have a data set representing the flight data. Right? So you have the flight, some of this flight, and you have a departure and destination. And you have a number of passengers coming in, and you have a flight. So what we're doing is we're now sending, this is the individual events. So imagine that we have some kind of telemetry coming from airport. They're capturing this one, and then we're sending on the fly in real time. Just that we're just not doing manually. So we do. Okay. And we have a topic called arrival. And we're sending. Right? So then when we do a show state, we do state here. And you can see that we actually now created here. Let me see here. We actually have this data coming in. Let me also we have this called data table here. Here, we have a CDG. Kind of messed up. Let me just clean this up here. Just the data here. So this is what happens when you do real time here. Just clean up the data here. Try again. Okay. So it's actually showing showing different data. Just happened to have probably kind of messed up here, but that's what happened. You're doing a real time. We're doing a real-time demo. Kind of probably messed up the data here. So, so the point is that this here we do is that this is the code that actually compute this data on the fly. So we actually get a table here, and then we actually compute this, add this flights and phrase on a real time.
I think it's actually correct because both go to sharp the go and you're showing the arrivals.
Oh yeah, that's right. So yeah, that's right. That's correct. I just got a little bit confused on there. So actually correct. And then now I can try to, let me just here, flight 2. And let's see here, we do, yes, that's right. So now we do data 2. Here is that we just added these two data sets, flight. So as the new data is coming in, we actually, so the state is maintaining in a real-time basis. Okay, and let me go here. All right, and then now I'll go to the last part, which is the what you call windowing-based calculation. So the problem, so the interesting part about the previous was that it's accumulator. So we actually increased the counting by one. But in terms of when you want to track the statistic, you want to do it in real time, which means that you want to get the statistic by every hour, for example. So idea is you want to compute get the top airport every hour. You want to, which airport actually has the most passengers and most flights. So in terms of that, we call the windowing process here, and we use this called simple tumbling window. And so before we had this state divided in terms of simple state, but the states are now split that into different windows. So between 9 a.m. to 10 a.m., we have this one is same here table, 10 a.m. to 11, different tables. And so what happened is that when windows are closed, those get flushed down, and we do another calculation. Okay, and hopefully that goes here, the last one here. All right. Okay. So in this case, we have this called flush aggregated, and what this thing does is that we get all this when the windows close, we get events, and we compute the top 3 airport. And hopefully this gets a little bit better here. Okay, so do show state, same thing, nothing here. Okay, so, and what we're gonna listen for is we have this called top 3 most busy airport. Oh yeah, that's right, thanks. All right, and then we have data set, okay. So the difference is previous is that we have a time. So previous data set is just the data. So you don't know when the data was produced. Now we're going to make it more realistic. So we have a flight data coming here, and this is the data when that was produced by some kind of telemetry. So we use that to compute the window-based. Okay, so I think we have to here. So we do the same thing. Okay, so in that case, the difference is that state variables, yes, all right, state. Let me see. There we go. Just type this one here. Compute. Let me just, yeah. All right, let me see why. Let me try again. This is the easiest way to do it. There we go. And you see flight arrival, and if we do here, you can see the airport and the time window when this was, because they're all aligned to the same window. You can see these windows are aligned here, and number of flights, and passengers. Now we do the last demo here. We have another data to here. And what happened is that then, because this data set will be sitting there in the window, and when we produce this data set here, that will close the window because we use a watermark to compute that value here. And you see this coming here, top 3 based on the previous one. So those are top three. And then if you see, those new data will overwrite the previous timetable. Okay. I think that's the part of the demo, and I'm just closing this one here. So we have a lot more features. The SSDK is still in a preview, so we are looking for a lot of feedbacks on the different use case. And I think we ran out of questions, but happy to answer questions after.